Hello everyone, and welcome to this mini video series in which we will be discussing the rudimentary primitive model of the arithmetic logic unit 8-bit chipset. We will attempt to provide a rough explanation for the role as well as the interplay between each of these components on the 8-bit chipset.
Throughout this discussion, we will refer to computer architecture hardware components that comprises the core functionality of executing a program as chipset. Our goal throughout this discussion is to explore the role that each hardware component plays and the interplay between them to understand the different computational models. Thus, we need a broader understanding of the processes involved during programming and the procedures and computational steps taking place on the hardware level during the lifecycle of a program. This will provide us with insight about the different types of computational models, the interplay between them as well as the usages and limitations around each. More specifically, we want to understand the aspects relating to the instructional computational model and its interaction and manipulation of bits of data. In the instructional model of computation, the random access memory plays the role of storing data, that is its only function on the chipset. The data stored on the random access memory is seemingly random bits of data in the form of binary. Keep in mind, the reason for using binary format to encode and manipulate data in computer memory is due to the factors including the following. 1. The states of a transistor can be 0 or 1, which is interpreted as on, or off, yes, or no, or true, or false, in the interpretation model of computation. On the hardware level, instruction model of computation, this corresponds to the transistor blocking off or passing through a current through the circuit component. 2. The states of data can also be used to encode the concept of decimal base 10 numbers by conversion to binary base 2 number format and can be further manipulated using binary arithmetic. In particular, we are interested in how to encode integers, signed integers and fractions. 3. The speed to switch between states 0 or 1 is much faster than primitive logic gate designs, using the vacuum tube architecture from the mid-19s. 4. The advent of the transistor-based CPU architecture and the microscale circuitry engineering of its design gave rise to mass production of more powerful computing devices, such as your phone. The CPU takes the role of performing arithmetic and Boolean logic on the data. It is designed and physically hardwired to add, subtract, multiply, divide and perform any arithmetic binary calculations and Boolean algebra on bits of data during program runtime. It is important to understand that any chunk of data stored on the RAM could potentially represent anything. The chunk of data ascertains meaning via the program language type interpretation system. For example, the sequence of bits 10100110 could represent an integer or a decimal float or any other type of object variable, depending on how it is declared and initialized in the program's type syntax. More detail about this later. The arithmetic logic unit, ALU, is a subcomponent of the CPU which performs the binary arithmetic, while the remainder of the CPU handles the Boolean logic of a program and input-output I/O processes.
So let us attempt to interpret what my robot girlfriend was trying to explain in more relatable, human-friendly terms. The CPU is an engineering masterpiece born from the marriage between the disciplines, or the intersection between the fields of the theory of mathematical logic and the application of transistor physics, to capture or model constructs from the mathematical framework of logic into digital transistor gates for emulating decision-making processes, quote-unquote deduction or deductive reasoning, throughout the programming and procedural design process. In other words, we as programmers are interested in using the underlying provided hardware's computational capabilities to emulate procedural tasks by abstracting away from the machine-level processes, though we still must understand the procedures taking place on the chipset. In other words, CPU engineers borrow important concepts from mathematical logic and implement these concepts using transistor physics and logic gate design. So, in other words, on the nanoscale, the CPU is manufactured specifically to comprise of transistors, gates, in the order of millions or billions to emulate, execute the decision-making process of a program's instructions. The mathematical framework of Boolean algebra and Boolean arithmetic are responsible, respectively, for capturing the ideas behind reasoning, using if statements and the likes, as well as the arithmetic manipulation of data in terms of ones and zeros. The IEEE 9191A standard for logic gate schematics are used to encode some of the transistor gates functionality built into the CPU and provides an abstract representation for the operations that take place on the CPU in terms of Boolean algebra and logic. The transistors exist both on the RAM as well as on the CPU for distinct or different purposes. Transistors on the RAM are responsible for storing the state of a piece or chunk of data in terms of ones and zeros, while in contrast, the transistors on the CPU are used for the following purposes: either to pass through a current in a logic gate or divert the current in a logic gate to a different conducting branch, or block off a current in a logic gate to simulate the idea of negation of a bit, a logical operation. These are basic mechanical arithmetic operations performed at the lowest level of the hardware. All of these processes are taking place on the microchip in a very short or brief amount of time during program execution runtime. The fact that we have millions or billions of transistors to our disposal is what gives us a massive amount of computing power at our fingertips, because we don't have to think about some of the smaller tasks or macros taking place on the instructional level of the hardware. Micros. Pun intended. In other words, by arranging the transistors into different configurations comprising of more primitive Boolean algebra hardwired as logic gates, we can build more complex operations or macros and algorithms, albeit hardwired. Keep in mind, a macro is essentially just a combination of smaller, more primitive subroutines. In other words, a sequence of operations that together perform a more complete or a whole task. For example, sorting items and then find the largest item among all can be combined into a single, more direct task. It is finding the largest item among a given collection of things. Another very important historic aspect of the evolution of computer engineering and design is the leap from non-programmable computers to reprogrammable computers, an engineering feat in which the very respectable John von Neumann has had a hand in the design of its computer architecture. In other words, the inability for hardwired static circuitry responsible for a single procedure that cannot be used for any other purpose other than for which the finite-state machine is designed or built for in the first place, such as household appliances, unlike the TI-84 Plus series calculator chips that may allow its users to redefine or change the program that it is designed to do. The stack model of computation essentially restricts its attention to the RAM and the storing of data in terms of binary bits. The interplay between the stack model of computation and the lambda or interpretation model of computation is analogous to the interaction between the RAM and the program or procedural script. In other words, these seemingly random bits or chunks of zeros and ones do not have any inherent meaning or type associated to it, in the sense that the computer does not really know what type of data it's dealing with, unless we associate with that specific chunk of data at that specified memory address a particular type of data in the programming language syntax. For example, an integer variable is usually declared using the int keyword and associates with this declared variable the int data type. Similarly, we could have an employee or student object variable defined as a class instance within a program's memory. Before concluding the general overview or discussion about computers and their architecture, we want to honor all the very gifted people at IBM and Bell Labs who have invested their brilliance into the modern day world of computing, as well as the important physics contributions for achieving our modern day PCs. I mean, we have mostly spoken about transistors and such in this episode, but keep in mind all the other engineering feats and physics that made the digital machine alive or possible in the first place. Sort of like Frankenstein, you know, piece by piece, component by component, the computer is stitched together through the intricate specialization of each hardware component. For example, the power supply unit, comprising mostly of transformers and capacitors for controlling the power, voltage and current of very delicate and small electronic components on the motherboard and the rest of the chipset, is not generally a component that we take into consideration when defining programmatic procedures. In other words, electrical engineers provide a starting point for us to further explore and write interesting code on this existing hardware framework with little hindrance or care, irrespective of whether we have an in-depth understanding of the hardware or not. This is what gives us the ability to simulate a game world or perform statistical analysis on a huge sample space. It's the abstraction away from the hardware that provides us with a large degree of freedom to do with the computational device whatever we may please. Such is the brilliance of innovation of science and those who have contributed and invested ingenuity into the evolution of hardware and technology. But we as programmers try to take advantage of already existing technology and then try to improve upon it in a programmatic sense. Let us take a brief tour through the evolution of the computer by visiting the following Wikipedia articles. Logic and logic gates. Logical theories and constructs encoded into circuitry. Boolean algebra. Boolean algebra provides the framework for computational logic and the arithmetic framework for computation with transistor states. ENIAC. The first reprogrammable computer. TI-84 Plus series calculator chip. Texas Instruments handheld programmable computer using microscale electronics. Computer. General purpose desktop PC. Analytic engine. A primitive form of a computer for performing arithmetic operations and control flow or conditional branching. Analog computer. Like an oscilloscope for measuring frequency, or even a simple thermometer or a microphone that records signal, any type of instrument for taking in and processing analog input data. Mechanical computer. A computer comprised of non-digital or no electronic components, for example, a gear mechanism or hydraulic switches. Microcomputer. The shrinking of hardware components through innovative ideas from physics applied to transistors and digital gate design. Personal computer. A household computational device. Stored program computer. A computational device that stores the program's instructions on board. Von Neumann architecture. Also known as Princeton architecture. An instructional model of computer architecture. Harvard architecture. An innovative computer architectural insight for separating storage and program instructions. Power supply unit. A computer hardware component for supplying electric current and charge to the computational device. That's all I have to say for this episode. Next we will talk a little bit more about the binary arithmetic, the RAM, and the stack model of computation.